So, welcome everyone. This is Operate First Data Science Meetup number 10. And today we have Selbi, who is a software engineer and who is going to talk about distributed ML workloads on OpenShift. So, over to you, Selbi.
Thank you so much. I'm just going to share my screen. Entire screen. Hope you guys can see the screen. So today we'll be talking about the distributed training across multiple GPU nodes. My name is Selbi. I'm a software engineer in AI services at Red Hat. I work with Red Hat OpenShift Data Science and our partners, trying to bring them on it. So today, before I go into my demo details, I would like to give a short introduction. So as we all know, the datasets and models are getting bigger, for which we need a more powerful and more efficient GPUs. So the need for that is rapidly increasing. And so, for example, our one GPU, we need more GPUs because we have bigger datasets and models. What we usually do is we add more GPUs onto the same node that we have, or the same machine. But at some point, we're going to reach the limitations of the hardware itself, of the housing, so where we need to actually place by maybe more nodes and more GPUs, so we can actually have a multi-node setting. So the goal of this demo is not necessarily to show that we can do a multi-GPU training, but it's actually a multi-node GPU training that allows for utilization of all available resources to us in a certain cluster, for example. And the setting that I will be using today is on OpenShift. So I have NVIDIA GPU operator and Kubeflow operators installed via Operator Hub. And what I'm going to do is I'm going to implement my model training with PyTorch. And the important function in PyTorch is the distributed data parallel. And what I will do is deploy containerized machine learning in PyTorch via Kubeflow. Kubeflow has a CRD called PyTorch job. And essentially what it will do is it will take the data set that I have through PyTorch and it will distribute it across the number of GPUs that I have. In this specific cluster that I have, is I have two nodes and each node has one GPU on it. And what PyTorch job will do is it will distribute this PyTorch ML training that I have across two nodes, and it will initiate a pod on each node. And that one pod would be the master pod, another one would be the worker pod. So these two pods would essentially do master pod or essentially what we'll do is orchestrate the training, performing tasks, and also performing tasks like checkpointing the model, right? So it's kind of like a reference point for all other workers that are actually doing the work. In this case, both the worker pod and the master pod will both do the work of training the model. And the data is evenly distributed between these two pods, and model is actually replicated on each pod. And the gradients are averaged from each GPU during the backwards pass. And now, let me show the files themselves. So first, I wanted to go through the image that I'm using. So the very base image that I'm using is from NVIDIA. It's a CUDA image. It's an image that has the CUDA installed on UBI. And on top of that, I install Python and also install the PyTorch. So this is kind of like my base image. And on top of that, what I do is I create an environment where I copy my script from my repo into this image, essentially, which is main.py. And within that same container, whenever it's created, I automatically execute the script, main.py. So now let's look at the main.py, which is the PyTorch code or PyTorch script that is getting executed. So here in the beginning, I just create a very simple model, convolutional net model with 2 layers. And the important thing here is the distributed data parallel. This is a PyTorch function that allows for distributing the data and replicating the model on each data or subset of that data set and performing the training. I'm using a very simple MNIST data set. And it works in conjunction with distributed init process group, which is this one, and also distributed sampler. So distributed sampler, what it does is actually divides that data set depending on how many GPUs we have or number of processes that we have. And in this case, we kind of define it right here. And the other important part of this is this initialized process group function of the PyTorch. What it does is basically ensures that every process is able to coordinate to the master. But how do we know what the master is by setting this environmental keys. And the master address, master port, rank, and world size. The world size is the number of GPUs that we have in total, right? So in this case, we have 2 of them. Each GPU is on a separate node. And we give the ranking for each GPU from 0 to world size -1. So the rank 0 will always be the master one, and whatever other ones will be the worker nodes or worker pods. And in this case, we also specify what's the master address, IP address of the one of the master one, which has the rank of 0, and the port number. And all of this will be set up, and this initialized process group is going to read that and ensure that every process or every GPU is able to coordinate through a master GPU using the same IP address and port. They basically will be able to communicate with each other by sharing their location. And the backend that we're going to use is NCCL. It's specifically for GPUs. There's 2 others, Glue and NPI. And Glue is more for CPUs, and NPI is more for high-performance clusters, high-performance computing clusters. So after that, what we do is we get the data set, load it, sample it, and we specify the backward like optimize it and stuff like that. And eventually, we basically compute at each epoch what's the loss that we have, and we record the time that it's completed, and we're going to do the 20 epochs. So this is the script that we will be executing, and this is the Kubeflow part where we have the PyTorch job CRD. So here we can see the PyTorch job. We specify the name, specify the namespace, and here we specify how many GPUs we're going to run on. So in this case, because we have only one, we have 2 GPU nodes with each one GPU, so a total of 2 GPUs. We're going to specify one of them as a master and the other one as a worker. But in case if we had, like, let's say, theoretically we had one, like if we had like 5 GPUs, we'd say like master replica 1 and worker replica 4 in that case, and we'll kind of create all these pods automatically. Then specify which image we're going to use, which I showed you guys earlier, and we request 1 GPU for master and 1 GPU for worker. So now let's go to the cluster. So this is the cluster. It's I can have the completed ones just to show you guys later the logs. And so here I have that YAML file that I showed you guys earlier with a name replica with 1 master and 1 worker. And I'm gonna apply it. And we can see that automatically it creates the master pod and a worker pod, as I mentioned earlier. And if we go into the master and into the logs, I mentioned earlier as well that the master pod is not only used for coordinating, orchestrating the training between other worker pods, but it also does the work itself as well. And you can see that it downloaded the data, and now it's going through the epochs. And you can see that the loss is decreasing as we want it to be. And we can take a look at the worker pod as well. And we have the same exact logs because they communicate with each other. And you can see that the loss is going down. The other important part that we can see is if we go to environment, we see that the master port is basically the IP address of the IP address and port of the master pod that we have. World size is the total number of GPUs that we have, which is 2, and the rank of this one is 1, which also means the rank of the master should be 0, right? So if we go to the environment, you can see that it's set correctly as well. So at times we can also double check that it actually is on GPUs. If we go to the terminal and we do NVIDIA SMI, we can see that it's running on Tesla K80 with a GPU utilization of around 56 at this point. And you can do the same thing with the worker node and check it. And you see that the GPU utilization is a lot higher in the worker one, and it's 97%. Yeah, then it's going to keep running all these. How many epochs have we finished now? We're epoch number 7. I'll just show you guys the ones that is already done. These two have been completed before. And let's go to the logs. In this case, the training was complete in 20 epochs, and as we can see, the loss is decreasing as we wanted it. And the training was completed in 8 minutes and 54 seconds. Let me go back to the presentation. Before I show the additional resources and stuff, I just also wanted to show an example where I ran it on 2 nodes with 4 GPUs each. It was done like a few months ago. Here, as you can see, there is a master pod on one GPU, and the rest of so it had 8 GPUs total. The rest of the 7 GPUs had the workers on them. So this is essentially how it will work if you have like a bigger setting where we have 7 workers coordinating with each other with a master pod. And the beautiful thing about those Kubeflow and PyTorch job CRD is that it's actually agnostic to your setup. Like, do you have like 2 nodes with 4 GPUs each, or do you have 8 nodes with 1 GPU each? It's kind of like, it's completely agnostic to it. It just determines how many GPUs you have, and it automatically runs on them, which is kind of a really nice feature. And you can see here, the master node has a rank of 0, and we have a total 8 GPUs. For example, worker here has a rank of 6, because I mentioned earlier, it's going to be labeled, it's going to rank from 0 to world size -1. And here you can see that all these 20 epochs obviously were done a lot faster because there's more GPUs processing it. It was done in 1 minute and 8 seconds. I just wanted to thank you guys for listening. Here I provide some additional resources on how to install the ODH, Kubeflow, and Nuryyeva operator, and also more references on the PyTorch job CRD of Kubeflow, and also the distributed data parallel function of PyTorch in more detail. And I'll take any questions now.
Thank you, Selbi, for this awesome presentations. So if anybody have any questions, feel free to raise your hand and ask it. Yep, Michael.
Hey, Selbi, awesome. This is a great presentation. Thank you so much. One question that I had, just looking at the slide from the beginning, was it seemed like the 2 operators that were required was just Kubeflow and the NVIDIA operator. Is this currently like part of like default Open Data Hub, or is this an addition to what's in the Open Data Hub operator?
Open Data Hub operator doesn't have the NVIDIA GPU operator, so that has to be installed separately.
Right.
Kubeflow can be, like, you can, going through the manifest, you can actually install the Kubeflow and the components of the Kubeflow that you want, if you don't want like the entire Kubeflow to be installed. You can specify that you want specifically the PyTorch job, and there's also for TensorFlow as well, there's a TF job CRD. You can through manifest basically specify which ones you want.
Cool, awesome. So yeah, so there's no issues then with just adding the NVIDIA operator on top of Open Data Hub?
That's correct, yeah.
Cool, awesome. Are there any limitations with this method, like the types of machine learning problems that can be parallelized in this way? Just wondering if you had any thoughts on that.
I know it can get a little bit tricky if you are, so in this case, I'm just parallelizing the data, and I'm replicating the model in each, I guess, subset of the data set. It can get a little bit more complicated and tricky to actually parallelize the model itself. So instead of replicating if you want to distribute it across several GPUs, that kind of can get tricky. It's possible, but it's not really well developed yet, as far as I know, from the people who actually try to do it.
Okay. So this approach, then it's like a time efficiency over a energy efficiency if you're just training it across multiple models or multiple clusters at the same time.
So technically, it's always honestly faster to do it. But if I have like 2 GPUs in one node, it's of course going to be faster doing it within one node. But I guess this kind of shows that you're not really limited to just one node, but you can do it on several nodes with several GPUs. It's kind of like not necessarily making it more efficient over if it's all in one node, but it's kind of, if you have several nodes, how can you take advantage of all of them? Basically all the resources that are available to you and not be limited to just one node.
Cool. Awesome. Thank you.
Anybody have any more questions to Selbi?
What clouds are you using this on? What, in terms of like cloud providers?
So I tried it on AWS before, but this one I think is the one that was provided to me by Operate First, which is the not the astronomy one.
So I think it's like OS Climate one or something.
Yeah, OS Climate one.
So yeah, Leonard, this is part of the Operate First, like open cloud infrastructure stuff. So this is an environment that's pretty much everyone, but definitely everyone here has access to.
Yeah.
Well, if anybody doesn't have any more questions, I'd like to once again thank Selbi for this wonderful presentation, and we'll meet you again in the next 2 weeks for the next data science or Operate First data science meetup. Thank you everyone for your presence.